Hello, this is the section 13.2 lesson. For this lesson you will need to print the worksheet titled Hypothesis Testing Tables from the section 13.2 lesson folder. This worksheet contains all the tables that you will need for these different hypothesis tests. You'll want to hold on to this worksheet to use it for the quizzes as well as the last test. You will not need your calculator for this lesson. Alright, let's start off with a claim. The mosquitoes in my backyard are worse than the mosquitoes in my front yard. Okay. Well, that sounds like a claim we have seen before. So in order to test this, what I might do is count the number of mosquitoes in the front and backyard on each of 12 evenings. So I go out 12 different evenings, I stand in the front yard, count mosquitoes, and then I go to the backyard and I count mosquitoes. And then I use that data to test the claim that the mean from the backyard is greater than the mean from the front yard using a two-sample t-test. That's what we did back in section 9.3. That data would seem to fit this. Everything sounds reasonable. However, there's a real serious problem here. How do I count the number of mosquitoes? That would be very difficult, if not impossible, to do. So this approach doesn't seem reasonable or at all feasible. So here's a possible solution. Instead of counting mosquitoes, what I can do is just stand in each yard for 5 minutes on 12 different evenings and swap mosquitoes, and then record which yard appears to have more mosquitoes, either the front yard or the backyard. I don't actually have to count mosquitoes, I just have to assess relatively which one appears to have more. So here's some data that I might collect. I record just a plus or minus sign, where a plus sign means that the backyard has more mosquitoes, a minus sign means that the backyard has fewer mosquitoes. So on the first evening my backyard had more mosquitoes, second backyard had more, third evening the backyard had fewer, etc. So here's the data that I have collected. Now what we're doing when we're swatting mosquitoes is we are observing the differences in the number of mosquitoes. And our data is really the sign of the number in the backyard minus the number in the front yard. If the number in the backyard is greater, then this difference will be positive. So we have a positive sign for our data. If the number in the backyard is smaller, then I have a sign of negative. Well, let's talk about the rationale behind how we're going to analyze this data. If the claim were true, meaning if I really had more mosquitoes in my backyard than in the front yard, then I would expect to have more plus signs than minus signs. Well, if I look at my data, that's exactly what I have. I have 9 plus signs and 3 minus signs, so my data appears to support the claim. Well, if I were to line up all the differences from the population of all evenings, the one in the middle would be positive. Right? As if I have more plus signs than minus signs, I line them up from smallest to largest, the one right in the middle would be positive, so I should have a plus sign in the middle. Well, we have a term for the one right in the middle, call it the median. The median, remember, was if we had a set of data, we line them up from smallest to largest. The one right in the middle is the median. So if the claim were true, then the median would be positive. Okay. So let's set up our hypotheses. Here's our claim: the mosquitoes in my backyard are worse than the mosquitoes in my front yard. So the claim in mathematical notation is that the median of the differences is greater than 0. Well, if false, then the median would be less than or equal to 0. My null hypothesis is that the median equals 0, and then my alternative is that the median is greater than 0. So here my population parameter is the population median. We won't use a symbol for median, we'll just call it the median. So there's my null and alternative hypotheses. Okay. Now to further analyze this data, we're going to do what we call a sign test. And to do this sign test, there aren't any formulas or anything we have to do. We let x equal the number of times the less frequent sign occurs. And n is the total number of positive and negative signs combined. If n is less than or equal to 25, then the test statistic is simply x. There's no formula that I have to use. All I have to do is count plus or minus signs. Now if n is greater than 25, there's a slightly more complex way of doing this test, but we're not going to get into that. So if I look back at my data, I see that I've got 12 plus or minus signs, so n is 12. I see I have 3 negative signs and 9 positive signs, and so x is 3, the number of times the less frequent sign occurs. So there's my test statistic, x equals 3. That's all I need. Now, to come to our critical or our technical conclusion, we're going to use a traditional method similar to what we did back in section 11.2. We're going to compare our test statistic to a critical value and then reject or do not reject the null hypothesis based on the comparison to the critical value. Now our critical value comes from this table A7, which is on that worksheet hypothesis testing tables. Along the left-hand side of this table we see n, and across the top we have alpha. Now below alpha we see several different possible values, 0.005, 0.01, 0.025, 0.05, 0.10, and then right below those numbers we have either one tail or two tail. Now typically we're going to use alpha to be 0.05, so we're going to be using either that column on the right or the one right next to it. But to determine if we're going to use a one tail or two tail, we need to look at the inequality that appears in the alternative hypothesis. If the alternative hypothesis has a not equal to sign, then we have a two-tail test. If the alternative hypothesis has a less than or a greater than sign, then it's a one-tail test. Okay. Well, in this example, our alternative hypothesis is that the median is greater than 0. So we have a greater than sign, so this is a one-tail test. So therefore we're going to be using 0.05 one-tail, which is in that right-hand column. Okay. So we go to that right-hand column and then down to n equals 12, and we get our critical value, which is 2. So that's our critical value. Now here's our criteria for rejecting or not rejecting the null hypothesis. We reject the null hypothesis if x is less than or equal to the critical value. We do not reject the null hypothesis if x is greater than the critical value. So in this case, x is equal to 3. 3 is greater than 2, and so we do not reject the null hypothesis. So there's our technical conclusion. Now, we word the final conclusion just like we've done in every other hypothesis test. The original claim did not contain equality because it's that the median is greater than 0, so we go down. Do you reject the null hypothesis? No, we do not. So there is not sufficient sample evidence to support the claim that the mosquitoes in my backyard are worse than the mosquitoes in my front yard. So at first glance our sample data appeared to support the claim. However, the strength of that support was not strong enough to conclude that it does indeed support the claim. Now let's talk about the requirements for this type of test, and there's only one. The sample data are random. That's our only requirement. There is no requirement that the sample data come from a population with a particular distribution, such as a normal distribution. So for this reason, this type of test is what we call a non-parametric or a distribution-free test. Now this type of test is nice because there's no complicated requirements to check if we've met, and so we're going to be able to apply this type of test to sets of data that we couldn't apply other types of tests to. And we're going to illustrate this in the third example. Let's look at another example of using the sign test. In 1908, William Gossett published the article "The Probable Error of a Mean" under the pseudonym of Student. He included the data below, which gives the yields of corn from two different seeds planted on adjacent plots of land. Our two types of seeds are called regular and kiln-dried, and I honestly don't know the difference between the two. So on one plat of land we planted some regular seeds, and then right next to that we planted some kiln-dried seeds. On that first adjacent plots of land, the regular seeds yield a yield of 1,903 pounds, and the kiln-dried yielded 2,009 pounds. On another plot of land, we planted some more regular seeds, and then right next to that we planted some more kiln-dried seeds. There, the regular seeds yielded 1,935 pounds, the kiln-dried was 1,915 pounds, etc. So we got all these different plots of land. We planted regular right next to kiln-dried, and we measured their yield and recorded them. What we're interested in here is determining, do the regular seeds do better than the kiln-dried, or do the kiln-dried do better than the regular, or maybe are they the same? Well, here's the claim that we're going to test. There is no difference between the yields from the regular and the kiln-dried seeds. In other words, we're claiming that there's just not a lot of difference between these two types of seeds. Well, in order to do this, we notice our data is not in the form of plus or minus signs. So in order to do the sign test, we've got to convert things over to plus or minus signs. And what we're going to do here is calculate the sign of the yield from the regular minus the yield from the kiln-dried. So for that first plot of land, we're going to take the 1903 minus the 2009 and record simply the sign. The exact value of that difference doesn't really matter. We're just interested in the sign. So for that first one, notice we take a smaller number minus a larger number, so the difference is going to be negative. So we record a negative sign there. In that second plot, we have a bigger number minus a smaller number, and so the difference is going to be positive, so on and so forth. So we don't need to actually do the arithmetic on our calculator, be real precise about it. All we need to do is look at, are we taking a small number minus a large number, or a large number minus a smaller number, and record the sign. So there's the plus and minus signs that we're going to be working with. So again, here's our claim. There's no difference between the regular and the kiln-dried seeds. Well, if this claim were true, then half of the differences would be positive and half would be negative. So if there's no difference, then about half the time the regular would do better than the kiln-dried, and about the other half of the time the kiln-dried would do better. So half those differences would be positive, half would be negative. So if I were to line up all those differences from smallest to largest, then the one right in the middle would be 0. In other words, the median would be 0. So let's set up our hypotheses. My claim in mathematical notation is that the mean of those differences would be equal to 0. Well, if false, then the median is not equal to 0. So our null is that the median equals 0, and the alternative is that the median is not equal to 0. So now we need to do our sign test. Again, we're not looking at those actual numbers there in the top two rows. All we're interested in is the plus and minus signs. So notice that we have there 4 plus signs, 7 negative signs. So n is 11 and x is 4. So there's my test statistic, x equals 4. Now we'll get our critical value from this table A7. There's our criteria at the top of the right-hand column. Now notice here that our alternative hypothesis is that the median is not equal to 0, and so we have a two-tailed test. So if we use alpha as 0.05, two-tailed test, we're going to use that column right next to the right-hand column. And n is 11, so we go down to row 11, that third column, and so our critical value is 1. Now our test statistic x is 4. That is greater than the critical value of 1, so we do not reject the null hypothesis. That's our technical conclusion. Word the final conclusion the same way. The original claim did contain equality, because as the median equals 0. Do you reject it? No, we do not. So there is not sufficient evidence to warrant rejection of the claim that there is no difference between the yields from the regular and the kiln-dried seeds. Now this conclusion is a little bit complicated because we got almost a double negative going on there. We do not reject the claim of no difference. So in other words, it looks like there's not much difference between the two seeds, so the different seeds appear to give the same yields on average. Doesn't mean that they're always going to be exactly the same, but on average it looks like they're about the same. Now in our last example, we're going to look at a case where we can apply the sign test to some data that we can't apply another type of test to. So here's our claim. The mean number of boxes of cereal in houses in a town is 3. Now this is the same claim that we looked at in the section 6-7 activity, and we use this to illustrate what happens when the requirements were not met. And but here we're going to do a different type of test. Instead of doing confidence intervals, we're going to do a hypothesis test. Okay. So here's some data. We went out and we asked 11 different houses how many boxes of cereal they have. The first house had 10 boxes, the second had 1, the third had 2, etc. So my sample mean there is 2.2. The sample standard deviation is 2.94. Now this is a claim about a single population mean, so this appears to be a simple t-test that we talked about back in section 8.5. T-test dealt with a claim about a single population mean, so this looks like something we've done before. However, that test had these requirements. The sample must be random, the value of the population standard deviation is not known. The third one is the important one. Either the population is normally distributed or n is greater than 30. Well, in this case n was only 11, so we don't meet the second part of that requirement. To determine if the population is normally distributed, let's look at a normal quantile plot of that data. And remember, a quantile plot is a way of assessing normality or determining if our population is normally distributed. If those dots lie close to a straight line, then the population is normally distributed. If they do not lie close to a straight line, then the population is not normally distributed. Well, notice that those dots don't lie anywhere close to that straight line, so our population is not normally distributed. That means that third requirement is not met, so we cannot do a t-test to obtain valid results. So instead of doing a t-test, we're going to do a sign test. So to do a sign test, we're going to restate our claim a little differently. The median number of boxes of cereal in households in a town is 3. So instead of doing a claim about the mean, we're going to test about the median. Now this is not equivalent to the original claim, but it's very similar. So the claim in mathematical notation is that the median equals 3. If false, then it's not equal to 3. The null is that it equals 3, and the alternative is that it is not equal to 3. Okay. Now, in order to do the sign test, we need to get some plus and minus signs involved here. So our sign is going to be positive if the number of boxes is greater than 3, negative if it's less than 3, and 0 if it equals 3. So we see there our sign there, plus, minus, 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 0, minus, minus, minus. And so that's all there is to calculating our signs here. Now to get our test statistic, we see that we have only one plus sign, we have 9 negative signs, and we don't count that 0. That's neither positive nor negative, so we're just going to ignore it. So x is 1, n is 10. There's all I need to do my sign test. So now we'll get our critical value from this table A7. Our alternative hypothesis is that the median is not equal to 3, so this is a two-tailed test. If I use alpha 0.05, then I use that third column. N is 10, so I get my critical value of 1. Compare that to x. X is 1, which is indeed less than or equal to 1, and so I reject the null hypothesis. Here's my technical conclusion. Word the final conclusion the same way. The original claim did contain equality, and I did reject the null hypothesis. So there is sufficient evidence to warrant rejection of the claim that the median number of boxes of cereal in households in a town is 3. So I reject the claim that the median is 3. So in other words, the median does not appear to be 3. Now exactly what that median is, I don't know, but it doesn't appear to be 3. Now one thing we got to be careful of is to note that this does not imply that the mean is not 3. The mean and the median are not the same. They're very similar, but they're not identical. The median is not 3, but that doesn't imply that the mean is not 3. So that's it for this section. The homework is section 13.2.